Okay, so hello everyone. My name is Zhuo Chen, a rising sixth-year grad student at UCLA. I'm working with my advisors, Andrea Gaz and Tuan Do, in the Galactic Center group. And today I will be focusing on my works on the star formation history study of the Milky Way's nuclear star cluster. Okay, sorry. Oops. Okay, so as the closest galactic nucleus, the center of the Milky Way galaxy is the only resolved one, which allows to observe individual stars and study phenomena and physical processes that may be happening in many other galactic nuclei. And this extremely dense region brings a lot of exciting science questions. And today I will be focusing on the question of what the star formation history is of the Milky Way's nuclear star cluster. And this question is of great importance to help us understand how the formation of stars connects to the formation of the central supermassive black hole and the inner bulge, and also help us make more accurate predictions of the compact object remnants. The star formation history of the nuclear star cluster has been extensively probed over the last few decades. Previous studies suggest a very old population. This latest star formation history study by Fu et al. 2011 reported that over 80% of stars formed more than 5 GeV ago. And one missing ingredient of current star formation history studies is the metallicity information. So when modeling the cluster, age and metallicity always introduce some degeneracy. This is the HR diagram with K magnitude versus effective temperature. The solid lines here show the 10 GeV isochrones, while the dashed lines show the 3 GeV. And the two colors show the different metallicities. And generally, the stellar population can be interpreted as either old or high metallicity, so either solid blue or dashed orange. So ages of stars can only be confidently determined with metallicity constraints. And all previous studies on star formation history analysis have so far assumed a uniform solar metallicity due to limited measurements back then, just only a few stars. And in the latest star formation history study on the left plot, which also assumed solar metallicity, and you can see a population of cool faint stars in their sample could never be well constrained by any star formation events. And now the big progress is the more recent spectroscopic surveys presented a significant spread in metallicity of late-type stars from the nuclear star cluster, not consistent with the uniform solar assumption anymore. So now we have a large enough sample from the Gemini NIFS and the VLT KMOS in total with nearly 1,000 stars with metallicity measurements. So now we are ready to incorporate the metallicity back to the modeling and fully understand the star formation history. And this is how these two data sets are spatially distributed. The blue regions are from the Gemini NIFS deep survey with adaptive optics and closer to the center. And the large red region is the VLT KMOS wide field survey. And we are also working on two data sets for early type stars. And this is the very central region within the 0.5 parsec. And the boxes show our Galactic Center OSIRIS wide field survey using KEC. And the blue little squares show the additional early type stars from the VLT. For the methodology, generally I apply the forward modeling method and a Bayesian framework by comparing the observed sample to a synthetic cluster, which is the model and which is the data and the model. So for the data, I'm using the measurements of K magnitude, color, effective temperature, number of stars, and metallicity. for the model, I'm using the synthetic cluster generated with 7 free parameters listed above. And to generate such a synthetic cluster, I use the SPICY, an open source Python package from Hosek et al. 2020 to simulate the isochron and a single edge cluster as the output, given all the rest of the input properties in the white boxes. And the main contributions in this work are to, for the first time, add metallistic interpolation in the modeling, and also consider several models of star formation history candidates like multiple bursts or continuous star formation. And with carefully tested, very reliable feeder, we have finished the modeling of the star formation history for our 2 late type stars datasets. And here are the fitting results from the deep AO sample. The feeder prefers 2 bursts scenario compared to the rest of the star formation models. The burst 1, the majority part shown in the upper panels, account for around 92% of the total mass, was modeled to be 3.6 gig years with metal rich, the metallicity of 0.45. And the burst 2 accounts for the rest of the population with a relatively younger age and metal pool stars. And the fitting results with our more data from the further away wide field sample are consistent with what I'm showing here. And here is the comparison of the data and fitting. The background Hass diagram shows the combined model predicted cluster with fitting weights and overplotted with a deep sample in red crosses. And now we're able to fit, for the first time, the low temperature stars. And the observed dataset is well characterized by the modeled 2 bursts of star formation events, with the majority of the older, higher metallicity population and the relatively younger, low metallicity population. And then focusing on the Asian burst, this age of 3.6 gig years is actually younger than any previously reported cluster age for this Asian burst. Remember, like the latest star formation history study by Fu et al. 2011 reported that over 80% of stars formed more than 5 gig years ago. But they had the solar metallicity assumption. So to test and compare with that, here I fixed the metallicity to be solar and did another round of fitting shown in the bottom 2 panels. The fitting reports a median age of 7 gig years for this Asian burst. So the fixed solar metallicity assumption actually made the cluster twice as old. So with full consideration of metallicity, the age of the cluster is modeled to be half as young. The younger age reported here means that the nuclear star cluster would have less time to form. They must build up much faster, which would challenge the mutual evolutionary theory of the nuclear star cluster, the central supermassive black hole, and the bulge. This may also challenge the globular clusters in falling scenario of the nuclear star cluster formation, because they would have less time to accumulate these clusters as well. And now we're also working on the Keck-Osiris dataset of the central young stars and see how they could be affected. Another interesting outcome of the star formation history study is to result in the most accurate prediction so far of the number of compact objects, and then their merger rates too, like stellar mass black holes and neutron stars, which is important for interpreting gravitational wave detections like those from LIGO. And this plot shows the compact objects predictions using the star formation history derived in this work, shown in red, compared to the predictions if using the previously reported age and metallicity, shown in blue. And we can see the predicted number of neutron stars in this work decreases significantly by a factor of 3. And this will consequently influence the merger rates too. And such big difference emphasizes the necessity of a more accurate star formation history of the nuclear star cluster. And thanks for listening. I will leave my summary here and take questions.
All right, do we have any questions here from the audience?
Why that is, and do you have a sense of why the data prefers 2 bursts, and like how, because I assume there's more additional parameters for that, so do you consider something like the Bayesian evidence to, and does it make sense physically
Yes.
for the galaxy?
Right. So for the fitting, we tested like a different star formation history models, like a single burst, like a multiple bursts, like 2 or 3 or more, and or continuous star formation history. And now the fitter prefers the 2 bursts, and you can also see the 2 bursts like a relatively the majority part with higher metallicity and older age, and some like very few stars right here, and prefers low metallicity with low metallicity measurements, but still like relatively younger than the majority parts.
All right, any other questions from the audience?
Hi, I was just curious if you understand why only the neutron star number went down by a factor of 3, but the black hole and white dwarf number seem to stay relatively the same.
Sure. Yeah, that's a good question, because I was also exploring this right now, and according to my current understanding, it seems like the age influences the number of neutron stars a lot. So like one potential explanation is that the neutron stars, the lifetime or like formation time would be much younger than the rest. Would be like influenced a lot by the age. So like the age would affect a lot compared to like the number of black holes or the white dwarfs.
All right, well, if there are no more questions here, let's give a big round of applause.
Thank you.